For millennia, the history of naval architecture was a struggle for survival. Today, it is a demonstration of absolute dominance. How do you force 10,000 tons of steel to plane across the water like a speedboat? These vessels are often dismissed as mere floating palaces. This is a mistake. They are cathedrals of steel and glass designed to break the fundamental laws of hydrodynamics. The construction budget for a single unit frequently exceeds the gross domestic product of sovereign nations, but the true cost is measured in drag coefficients and propulsion loads. The ocean resists movement, gravity pulls down. The engineering challenge is to cheat both. We are stripping away the veneer of luxury to reveal the industrial beast underneath. Let us dissect the machine. To defeat physics, you must first master the coefficient of drag. Enter the Lionheart. Born in the Benetti shipyards of Livorno, this 63-meter titan is not designed for appearance, but for fluid dynamics. The construction is a hybrid cage, a hull of heavy steel for structural stiffness mated to a superstructure of lightweight aluminum. This disparity in density lowers the center of gravity, keeping the vessel upright against the ocean's lever arm. 3,000 tons of displacement. The hull does not ride over the waves, it forces them apart. As the twin Caterpillar engines engage, the bow cuts the water with surgical precision. The energy management is absolute. Stand on the lower deck at cruising speed. Silence. The vibration is so low you could balance a coin on the floorboards. But the real war is fought against motion. Beneath the waterline, active hydraulic fins extend. They act as underwater ailerons. Sensors detect a wave's impact in milliseconds. Before the ship can tilt, the hydraulics drive the fins against the flow, generating an equal and opposite counterforce. The massive beach club terraces unfold with the same hydraulic pressure, hovering inches above the waterline, but the interior luxury is secondary to the stability system keeping it level. The goal is static perfection, 0 degrees of roll. While traditional hulls attempt to climb over the swell, Motor Yacht A chooses a different path. It slices directly through. At 119 meters, the silhouette resembles a surfaced submarine or a polished blade. This is not a stylistic whim, it is a hydrodynamic scalpel. The inverted bow design eliminates the reserve buoyancy found on standard ships. Instead of riding the waves and crashing down, the stem pierces the water column. Vertical acceleration drops. The pitching motion vanishes. To the observer, it looks like a sci-fi prop. To the engineer, it is the most efficient solution for stabilizing 6,000 tons in a storm. The shell itself is a fortress. The glazing is 44 millimeters thick, engineered to withstand not just Atlantic pressure but close-range explosions. Behind the blast-proof glass and polished steel, the vessel operates as a closed loop. Advanced waste processing systems allow it to vanish into the ocean for weeks without releasing a single particle of residue. Total autonomy. While radical geometry slices through resistance, sometimes the engineering answer is simply brute force, raw kinetic energy. Meet Azzam. At 180 meters, it currently holds the world record for length. But strictly speaking, this is not a yacht. Mechanically, it is a missile frigate draped in civilian white paint. Physics dictates that a steel hull of this magnitude should be slow. Azzam ignores this law. It drives a floating mountain through the ocean at over 30 knots. 56 kilometers per hour. To achieve this defiance of inertia, engineers abandoned traditional propellers. They installed a hybrid heart. 2 massive diesel engines work in concert with 2 gas turbines derived directly from the aerospace industry. When the captain engages full throttle, the deep thrum of diesels is overtaken by a high-pitched scream, the sound of a jet fighter taking off. This 94,000 horsepower output is channeled into 4 high-pressure water jets. The mechanism is violent and precise. Giant intakes swallow tons of seawater every second. Titanium impellers compress the flow inside the tubes. The rear nozzles blast a coherent, solid column of water out the stern, with enough force to cut through concrete. It creates a thrust vector capable of moving 13,000 tons as if it were a speedboat. Yet, despite this mechanical violence at the waterline, the vibration inside the main hull is effectively 0. If the hull dictates hydrodynamics, the integration of glass into the structural frame fundamentally changes the physics of the superstructure. Meet the Al-Mirkab, 133 meters of steel and reinforced silicate. Here, the windows do not simply fill holes in the walls, they hold the walls together. Naval architects bonded multi-layered glass panels directly to the superstructure, creating a composite skin that significantly increases torsional rigidity. The glass bears the load. It fights the twisting forces of the ocean. Inside, the material engineering continues. While the decks are lined with rare marble, the true innovation lies in the movable bulkheads of the Sky Lounge. These mechanical walls slide on hidden tracks, instantly reconfiguring the geometry of the space from a state reception hall to a private enclosure. But static luxury requires kinetic force. To propel this 9,000-ton mass at 20 knots, the hull conceals a diesel-electric plant with an output exceeding 35,000 kilowatts. However, static loads from structural glass are incomparable to the shock impact of heavy aviation. At 162 meters, the Dubai demands a schizophrenic engineering approach. Deep inside the atrium, a circular glass staircase spirals through the decks, its steps embedded with LEDs that shift color temperature to match the circadian rhythm. Fragile, precise, but 7 decks above this delicate core, the superstructure is built for violence. The helipad is not merely a flat surface, it is a reinforced impact zone designed for heavy transport aircraft, 9 tons of metal dropping from the sky. When the landing gear slams down, the kinetic energy does not vanish, it travels. To stop the roof from buckling into the VIP suites, the upper deck utilizes a dense grid of high-tensile steel beams. They disperse the shockwave laterally, instant dissipation. While the frame resists impact, the systems fight thermodynamics. The vessel operates in the Persian Gulf, where ambient temperatures hit 50 degrees Celsius. Heat waves shimmer off the water. The steel hull bakes. Yet, the interior remains locked at 21 degrees. To maintain this 30-degree delta, the chillers generate a cooling capacity equivalent to a metropolitan shopping mall. It is a massive industrial freezer disguised as a palace. The rotors slow down. The helicopter wheels settle onto the non-slip deck. Beyond the external shock of aviation, a critical threat to stability comes from the internal liquid mass. This is the Dilbar. At 156 meters in length, it holds the world title for the largest superyacht by internal volume. Deep within the hull lies a 25-meter swimming pool holding 180 cubic meters of water, 180 tons of shifting fluid. If this mass moves uncontrolled, it creates the free surface effect. As the ship turns, water surges to the low side, shifting the center of gravity and risking a dangerous list. To prevent this, the vessel employs a complex network of compensation tanks. Sensors detect a roll in milliseconds. Computer-controlled baffles disrupt the momentum of the water, killing the wave before it hits the pool wall. Outside, the ocean might be churning, but the pool surface remains glass flat. Sustaining this active stabilization requires a power plant of industrial magnitude. The onboard diesel-electric system generates enough energy to light up a city of 40,000 people. Total output reaches 30,000 kilowatts. Managing liquid mass is complex, but controlling sound waves requires jeweled precision. Enter Al Said, a 155-meter Leviathan with a displacement of 16,000 tons. That is the weight of 2 Eiffel Towers floating on the ocean. Deep in the hull, high-torque propulsion systems push this steel island to 25 knots. The mechanical roar is immense. Yet directly above this industrial cacophony lies a sanctuary designed for zero acoustic interference, a concert hall built for an orchestra of 50 musicians. Steel transmits vibration 5 times faster than air, a nightmare for acoustics. To solve this, engineers executed a radical structural decoupling during the build. The auditorium does not touch the ship's primary skeleton, it floats. The entire room rests on a system of heavy-duty elastic mounts. These rubber and steel isolators act as a firewall for kinetic energy, absorbing the low-frequency thrum of the drive shafts before it reaches the stage. Outside, the propellers churn the water with thousands of horsepower. Inside, the isolation is so complete that the only sound is the slide of a bow across a violin string. Absolute silence. Complex architecture requires digital oversight. On the 147-meter Topaz, recently renamed A+, the crew is supported by a fiber optic nervous system. The vessel is longer than a standard football pitch, yet the network connects every corner instantly. It is a cybernetic organism. Data flows from thousands of sensors to the bridge, allowing officers to monitor every single valve and engine cycle in real time. This digital vigilance protects the comfort of the cinema and conference rooms below. The system feeds the zero-speed stabilizers. Sensors predict a roll before it happens. The computer calculates the counterforce. A signal fires, and the hydraulic actuators drive the fins against the current. Reaction is insufficient. A true superyacht must predict the roll. The 134-meter Serene, a flagship of the Italian Fincantieri shipyards, operates on this principle of anticipation. While standard hydraulic systems fight the waves, Serene's gyroscopic sensors read the ocean surface thousands of times per second. The computer builds a real-time model of the swell. Before the hull even begins to lift, the underwater fins change their angle of attack. The result is unnatural physics. A glass of water on the dining table remains perfectly flat, while the ocean outside rages. Static stability in a dynamic environment. This engineering extends below the waterline into the Nemo room. Here, the hull disappears. A viewing portal made of 12 centimeters of laminated glass holds back the Atlantic. This is not just a window, it is a transparent shield capable of withstanding pressure equivalent to a compact car resting on every square foot. Inside, there is no vibration from the engines. Visual silence. The contrast defines the vessel. While the exterior hull battles tropical heat exceeding 30 degrees Celsius, the interior engineering maintains a permanent winter. The onboard snow room generates real snowflakes at -10 degrees. The systems fight the salt, the heat, and the waves simultaneously. The result is total isolation from the external environment. The Atlantic is predictable physics. Human threats are chaos. At 162 meters, the Eclipse is less a luxury vessel and more a private frigate disguised in white paint. The superstructure is shielded by a radar-controlled missile defense system. The hull is plated with armor steel. The windows are multi-layered polycarbonate laminates, thick enough to halt a high-velocity sniper round. But the first line of defense is made of light. Distributed infrared sensors constantly scan the horizon for the optical signature of a specific curve, a camera lens. Detection triggers a millisecond response. A laser beam strikes the intruder's optic, a flash of white. The digital sensor is flooded with photons, burning the image into useless, overexposed static. If the perimeter is breached, the escape route lies underwater. A 3-person mini-submarine launches directly from an internal wet dock, diving beneath the keel without ever breaking the surface. Even the leisure facilities disguise heavy engineering. The main swimming pool floor rises on hydraulic jacks, draining the water in minutes to lock flush with the deck as a solid floor. Keeping this military-grade hardware operational requires a standing army of 70 crew members. The maintenance bill hits 50 million euros per year. That is roughly 137,000 euros every single day. Financial limits do not exist here. We utilized advanced artificial intelligence simulations to breach the hulls of these leviathans, visualizing engineering secrets usually hidden by strict security protocols. These are not merely yachts. They are independent city-states powered by industrial turbines. Now, the decision belongs to you. If you were the owner, which giant would you choose for a global circumnavigation? The raw volume of Dilbar or the tactical shield of Eclipse? Write your answer below. Subscribe now to initialize the next analysis.